Hello and welcome to the second part in the integral bit of the Introduction to Calculus. Today we're going to be talking about definite integration. So last video I covered indefinite integration, which is kind of how to find the antiderivative of a function. And today we're going to be talking about definite integration. Now, the same way that derivatives kind of have this idea of slope behind them, right? So if you have the derivative up here, would be higher because it's a steeper slope, and down here, right? Integration also has kind of a similar, well, not a similar, but it also has a geometric interpretation. An integral, if you have something like this, the integral gives you the area under the function, right? So this would be f of x, and I start at, for example, x equals 0, and I end at x equals 2. Then the area would be given by the integral of my function from 0 to 2. So down here you put down what you started, and then up here where you ended. So, those are also kind of called the bounds of the integral, right? So you start at 0, and it integrates this function up to 2, like that. So let's do an example to see how it works. It's kind of what do I do with these numbers up there, right? So what do we do with them? And to show that, we'll do an example. So we'll do an example of with the function x minus x cubed, and it's also nice to sketch the function when you're doing this kind of integration. So the function kind of goes like this, like so, and I want to find the area right here, so this area, right? So that's kind of the assignment. You might see this as the area bounded between the x-axis and the curve of f, or something like that. Alright, so this area, so first of all we need to find out what it's bounded by, right? Because we need to find the bounds of our integral. So for that we'll just solve for 0, right? So we'll solve f of x equals 0, that's where a function crosses the x-axis. So that's going to be x minus x cubed equals 0. Factoring out the x gives something like this, equal to 0. That gives me x equals 0. That's the way I draw it too. So x equals 0, that's obviously the first bound. And then the other one, that's going to be 1 equal to x squared, which is going to split up to x equals negative 1 or x equals 1. Now x equals negative 1, that's this part, obviously. So we don't really need that. So this is going to be the other bound, x equals 1. Going to be the other bound of the integral. So let's now integrate this function. So we'll note that down from 0 up to 1 of x minus x cubed dx. And first of all, what you just do is you just take the antiderivative of the function on the inside. So you just take the antiderivative of x minus x cubed. And you can actually just leave the plus c, so the added constant, you can leave that aside for now. That doesn't really matter when you're doing definite integrals. So you can leave that be, and you just take the antiderivative. So the antiderivative of this, I'm going to make use of the antiderivative power rule, if you will. So the new power, you divide by the new power, right? And this will become increase that by 1. That's going to be x to the 4th, and divide by the new power, like that. And then what I'm actually going to do is I'm going to enclose that in square brackets, like that. And then on the right I'll put down the bounds of the integral, like so. And this is just telling you to evaluate this inner expression, so the antiderivative of our function, at 1, and then subtract off it evaluated at 0. So I'll quickly explain what I mean. So first of all, you just evaluate the function at 1, right, at the upper part. It's going to be 1/2, 1 squared minus a fourth, 1 to the fourth. And it's going to be 1/2 minus a fourth, which is going to be just a fourth. And then I need to subtract off. So subtract off entirely the function evaluated at 0. So you plug in 0. It's going to be 0 squared, and then subtract off a fourth, 0 to the fourth. Now this is obviously entirely 0, so actually the area will now become just a fourth. And that's actually the real area, right? So so first of all, you search for the bounds of the integral, and that's dependent on the question, right? It depends what they're asking for what kind of area. It's always nice to sketch when you're doing those kinds of problems. And then we took the antiderivative of our function, and then we plugged in the bounds of the integral. So first of all, the upper bound, and then subtract off the lower bound. So if more generally I have a and b like that, and I can say that this definite integral will be the antiderivative, which I'll just denote as capital F. I'll quickly write that down like that. So that's first of all evaluate at the top integral, and I subtract it off the bottom like that. And you can also see that if you switch around these bounds, so you have b and then a, that's actually just, then it will be f of a minus f of b, which is just negative f of b minus f of a, which is, so it's negative a and b. So if when you switch around with the bounds, you just get the negative version of the integral like that, which is consequence to how you're doing how you're evaluating the integral, right? So let's do another example, because it's quite involved, this. Alright, so let's do an example. Yes, let's do an example. For example, we want to find the area. We want to do something like this. Alright, so we have this function g of x that's going to equal the square root of x, like that, minus 1. So minus 1 is just constant. And let me just sketch that real quick. It's going to be something like that. Alright, and the question is as follows. So we have, first of all, we have this area right here, which I'll just call phi. So that's phi. And then we also have an area right here bounded by the line x equals p. So we don't really know what it's bounded by. I mean, we know it's bounded by this, but we don't really know what it's bounded by on the right bit. And we'll call this area W. And the question is, for what p, so find p such that these two areas are the same. Right, so you can kind of think of an approach now. So first of all, we'd compute the area of phi, and then we'd see kind of by shifting this line around for what p the area of W is actually the same. So so let's do that, right? So let's try that approach. So first of all, we need to find the area of phi. So first, area of phi. And to do that, we're going to need to find where the function crosses the x-axis. So again, that's first of all doing the bounds of our integral. Now, kind of, you can already see that it crosses, or it's bounded by the y-axis right here. So our first bound is going to be 0, x equals 0. And then the second bound, that's x minus 1 equals 0. We're finding the intersect with the y-axis. Then the x square root of x equals 1, which is going to be x equals 1. Alright, so the area of phi, we now know the bounds. It's going to be from 0 to 1. And then we have to integrate g of x. Alright, so let's fill in g of x, square root of 1. Alright, and then I'm actually going to just split this up. I'll do like that. And this you can also do with definite integrals. You can also do it with just indefinite integrals, but it's fine for doing it with definite integrals. Alright. So this will be evaluate. That's going to be the new power is going to be 3/2, but we have to divide by the new power. So that's going to be 2/3 x square root x, right? Because we're increasing by a power. And then this one, you might be able to be a little bit puzzled by this, but if you remember the derivative of x, that's just equal to 1. So the antiderivative of 1, that's going to be x. So that's x, and evaluate that as well. Alright, so now we can plug all our values in, all our bounds. Be 2/3, 1 times 1 times square root of 1. Subtract off 2/3, and that's all times 0, right? I'm not going to write that out. And then I have to subtract off the entirety of, first of all, plug in 1, subtract off 0. So now I can plug this all in. That's 2/3, and then subtract off 1, which is going to be -1/3. Now this may seem puzzling, right? Why would it be -1/3? But that's actually because it's underneath the x-axis. So any area underneath the x-axis is going to be negative. And this is a little bit weird, but don't stress about it. We'll just take the absolute value, right? We'll just work with 1/3, and it'll be fine, right? So always look at the geometric interpretation. So if you really need to compute an area, you shouldn't say a -1/3, because that's not really an area, right? But if it's just a step in some algebra, then I would recommend keeping 1/3. Alright, so that's our first step done. So we found the area of V, and so now we need to find the area of W. And that's going to be the integral of g of x. Oh, excuse me, those bounds are not correct. It's going to be from 1, right? Because we start at the intersect, and then we have to go all the way up to p. So our upper bound is actually just a variable. That's going to be p. And then g of x dx, like that. So now I'll fill this in. I can just copy the integral from here, 2/3 x square root x from 1 to p. And then subtract off x evaluated at 1 and then p. Alright, so let's plug this in. Well, we know that, first of all, this is going to be 2/3, or excuse me, yeah, 2/3. And then I just have to plug in p, so that just becomes p. And then subtract off this evaluated 1, that's 2/3. I have to subtract off all of this, don't forget the brackets. First of all, evaluated at p, that's just p, and then subtract off 1. Alright, like this. So now, let's work this out really quickly. Like so. And then I have to distribute the negative. It's going to be -p plus 1. And then I group the like terms. And the -2/3 plus 1 is going to be plus 1/3. Actually, let me first of all do the -p. And then plus 1/3. So now I have this expression for the area of W, right? I have this expression for the area of W. Don't really know what to do with it yet. Well, actually, I do know what to do with it, because we want the area of V and W to be equal. So actually, we can set these two equal to each other. Look at that. And again, we won't do the negative here because it doesn't make a whole lot of sense. We'll just do the positive. So we'll do 2/3 p squared p. And then we have 1/3. And then that's going to be equal to positive 1/3. Because the area of W will come out as positive because it's above the x-axis, remember? Alright, so it's going to be equal to 1/3. And again, we can, so like right here, we can cancel the thirds. It's going to leave us with 2/3 p squared p, subtract off p, equal to 0. So first of all, we can factor out p. It's going to be 2/3 squared p minus 1 equal to 0, which is going to leave us with p equal to 0. But this is obviously wrong because it's just the same bounds as we had on V. So that won't work, right? So we can discard this one and see what we're left with. So always remember, don't always keep thinking about what you're actually doing, because the bound p equals 0, that doesn't make a whole lot of sense. It's not really what we're after. Alright, so let's continue here. So we have 2/3 square root of p minus 1, so we'll bring the 1 to the other side. Give me 2/3 square root of p equals to 1, and then do times 1.5, which is going to be 3/2, and then p is equal to square root, or actually no, that's not correct, 9 divided by 4, squaring both sides. And that is our final answer. So we've now seen that so we can actually say that the area of W is the same as the area of V for P equals 9 divided by 4. So that's kind of nice, and it kind of has to do with how the slope of the square root kind of it goes downwards, right? It's not as steep, which means the area increases a little bit less steeply. Right, so that's one of the applications of definite integrals. So you can have this kind of p action where you have a variable in the bounds, and then by evaluating it you can get you can solve for p and find out questions like this. You can also say, when is the area of W 2 times bigger than the area of V? That's still a valid question. You're just basically doing the same thing except with a factor of 2, right? So those kind of things. Alright, so now I want to show a similar but a bit of a different application for definite integrals, and it's finding the area between two graphs. So how would you do that? Alright, so let's draw this. Alright, so say I have, so I'll do a simple example. So this is going to be x squared, and then I'll have just y equals x, like that. So, and the question will be, what is the area like right here? What's that area going to be? Well, let's see, how can we approach this? Well, first of all, we can try to find the area of both just the area covered by x squared. So we have V is the area under x squared, and then I have W, so this is going to be V, and then W is the entire area, so that's going to be the area under y equals x. So I have two separate areas, and you may notice they both have the same bounds, right? They both end at two intersection points. Alright, so, and now you may notice that the blue area covered here is just the area of W subtract the area of V. Right, so you have two areas, and then the bit that doesn't overlap you just subtract off, like that. And more generally, you can say that the area between two curves is the integral between their intersection points of the outer. So the outer curve would be y equals x because it kind of goes above it. Subtract off the area of the inner curve. So a little more mathematically, that would be from a to b of f of x. It's going to be f of x, or excuse me, f of x dx, and then subtract off from a to b, because the bounds are the same, g of x, where, and then f of x must be bigger than g of x, right? Because f of x is kind of the outer function. So let's apply this to our problem here and see what we get. Alright, here we go. Alright, so let's first of all do the bounds. So first of all, the bounds, it's going to be x squared is equal to x squared minus x is 0. It's going to be x equals 0 or x equals 1, like that. Alright, so, and now we can plug those in. Alright, so we can do 0 to 1. F of x, that's our outer function, so our outer function, that's x dx. Subtract off our inner function, that's x squared. From 0 to 1, x squared dx. Alright, and we'll take the antiderivative, that's x squared divided by 2 from 0 to 1. subtract of x cubed divided by 3 from 0 to 1. Alright, so now we can plug this in. This becomes 1 over 2, and then the 0, obviously that just goes away. And then I have to enter in the 1, that's going to be 1/3. And the 0 again, that just vanishes because it's all x. Alright, and then a half minus a third, that's a sixth. So the area between these two is just a sixth. How nice is that? Alright, and that basically wraps it up. We've seen how you can compute the area underneath the curve using integration, definite integration. And we can see how this might apply to a little bit more complex problem with a parameter in it. And we've seen how it can be used to find the area between two curves, like that. Alright, thank you for watching, and I'll see you in the next part. Bye bye.